So I'm Cyrus. I'm going to start this presentation about design methodology for backhaul distribution on networks using the newly freed up white spaces. So I'm sure most of you in the room already know what this is about, but just in case, an outline of this talk would be an introduction about how white spaces came about and what is it actually. And then we're going to talk about regulatory backgrounds a little bit. And then we're going to try to answer the question of how much white space is actually available. And along that lines, we're going to try to fit it to a scenario and see how it works out. And of course, at the end, we have the conclusions and future directions. So first, an introduction. White spaces are basically newly freed bandwidth in the 700 megahertz region, and they're mostly high VHF and UHF. And after announcing that the FCC would free up such frequency, there has been a lot of interesting research going on in the cognitive radio field. So there are a couple of examples are spectrum management, spectrum sensing, and dynamic spectrum access, which are very interesting topics. We have a lot of good work on that.
I think we've had thesis defenses on all these topics the last couple of days.
So Samson did spectrum sensing, and would you describe yourself as if you had to describe the thesis you just did as
spectrum management?
You would call it management or access?
No, closer to management.
I think they're related, these two, to some extent.
And yours is neither of those? You think yours is management?
I think mine would be management more.
All right.
I'm guessing. So we're trying to answer this question: how can we use the white spaces within the rules that the FCC has given us? We will try doing this by using an example. For example, New Jersey has a test bed, and then try to calculate the white spaces available in that region, and then trying to apply it to a use case that we propose. So we're on slide 4, and so a bit of background. So in 1996, the FCC issued the DTV transition, as they call it, which meant that all the analog broadcasters needed to switch to digital transmission. And for that, the FCC gave them extra spectrum to sort of do both simultaneously, to keep the analog channel while transitioning to the digital transmission. And their justification for that was that we can get better picture resolution, better sound, better color, we can get HDTV, we can get surround system, and get multicasting, which basically means we can get a couple of channels out of one channel that you free up. And the most important for us, actually, result of this that it would free up a lot of spectrum, a lot of, as Professor Mondeon calls it, beachfront property spectrum. And this took until 2009, and after 2009 it was all digital, and we have the white spaces available from that date. Couple of desirable characteristics and why white spaces are actually desired. Well, first, the propagation, the frequency is low, so path loss is less, and we have more propagation. And second, for the same reasons, actually penetrates better around buildings or any obstacle. And the third is the bandwidth. There is a huge amount of bandwidth available in these frequencies, so this is very desirable. And a couple of issues around white spaces. The first, technical. Well, the broadcasters would definitely not like this to cause any interference in their region. And also, there are a lot of low-powered transmissions going around these white spaces, around these frequencies, which again is a technical issue to solve. And the political, again, comes back to technical. Basically, some people wanted to control the white spaces, some people wanted to, the broadcasters and the the licensed wireless microphones would try to actually prevent this from happening, because they were, of course, in danger of interference and and all that. So it was a lot of political battle there. And there's another issue of applications. There are dozens of applications that can be proposed for white spaces, as local as a small home connection, and as far as what we're trying to propose here, a backhaul for a network. So there are tons of applications for this. So now we want to go into the actual FCC's second report and order, which was the first official set of rules set out by the FCC. They gave some number of channels that are permitted for transmission. This is actually a table of the channels permitted. So it's between 2 and 51, with some exceptions. And also for the portable devices, which are smaller devices, it's only from 21 to 51. So they actually divided the TV band devices, which are the devices that are going to work in the white spaces, into two categories: portable or personal devices and fixed devices, and have different sets of rules for each of these. So as you can see, even the channels are different. Some channels are only fixed, allowed devices are only fixed, some are only portable, and some are a mix. And a couple of channels are emitted. For example, 37 is for astronomy. 3 and 4 are coincide with VHS videos and all that. And so they have a lot of provisions here. And all right, so sure. But now there's a recent ruling, which is in September 2010, which changes the rules. So the previous rules had some provisions for low-power TVs and wireless microphones, which operate unlicensed in the same region. Well, sensing had to be done, and you had to have geolocation, and then sensing requirements were there in some of these devices. But the recent ruling, after a lot of battle from different companies, actually omitted that rule. So they gave either one of these two channels right here, either 36 or 38, for wireless microphones use, and then omitted the sensing requirement that they had, which had a lot of issues around it. So other than this, they also have a protection rule, which is in terms of the space that can be used around these channels. So the limitations of the FCC are, again, the limited number of channels, which we gave in the previous table, and then there's the protection radius around each primary tower that they have, which no secondary white space, basically, transmission can be in that region. And also above that, there is this additional separation ring, which is a ring around that protection radius, where no secondary transmitter or tower can exist. This is actually what they give for this additional separation, that they actually have numbers there that you have to use and calculate, and just an illustration of this would be a TV tower with the protected radius and the extra ring around it. So as you can see, a secondary device, if secondary wants to transmit, the transmission will not exceed the protection radius, and the tower itself cannot go inside that ring. So this is how they've set it up. So for us to understand this and try to come up with the white spaces, we actually mapped each of these rules onto the map of New Jersey using Google Maps and some apps that it has inside it, and the FCC database that is available online. And we note that we also used New York, New Jersey, and Delaware for this, because many of the, for example, New York City towers actually span into New Jersey. So it still limits our space in New Jersey. So this is an example of how we mapped it. And note here would be that co-channel and adjacent channel transmission is different in terms of the space. So if you're using the same channel within that region, you're more limited than if you're using an adjacent channel. But you're still limited if you're using an adjacent channel. So as you can see, the diameter, the radius is more per channel. So to map this, we have an example. For example, these are 3 channels, and we're trying to calculate the available space for portable devices for white space. So as you can see, for 24, this is, for example, a tower over here, and this is its protected radius and extra ring around it. So this white area here is potentially we can potentially use this. And same goes for 25 and 26. But if you actually want to use 25, they have a rule, which is an adjacent channel rule, which says that if you want to use 25, you have to also consider 24 and 26 in using 25, which means that you have to superimpose all three of this, and wherever is left would actually be available for transmission. For portable devices, they say that the adjacent channel is available, but with lower power. But for fixed channels, it's completely off limits. So, as an example, this would be how it looks like in terms of where you can use wireless white spaces in portable devices. So this is completely prohibited, and the lighter green says that you can use it but with lower power, and the more greener, brighter green would say that this is completely available. So as you can see, it's very limited. And the same goes for fixed devices. The rings are more wide out, and again, if you want to use 25, you still have to superimpose all three, and this time you don't have any lower power or anything. You're completely blocked out here, so you only have these two small regions to work with in channel 25. So to further try to quantize this, basically, we went for a bandwidth database, and what we did was that we superimposed a 5 by 5 mile by 5 mile grid on top of the map of New Jersey, which gave us regions that we can calculate one by one. So, for example, in this region, as you can see, the blue cells are 25 is not available in the blue cells, and it is available in the green cells, and some are actually partially available. So, if we do this for each and every channel, we can come up with a database of which cell has how many channels and which channels available. And in doing this, this was our conclusion, that between 7 to 31 channels will be available everywhere in New Jersey. And each channel is 6 megahertz, so that's pretty easy to spell, 42 to 186 megahertz. And keep in mind that we only considered UHF for this study, and we did not consider the effect of low power TVs or any other transmitters that might be actually limiting a little bit. And this is the mapping of this 7 to 31 channels available. Well, obviously you can see that around New York City and Philadelphia it's less, and top and bottom more. So all this comes down to a database looking like this. This is just a snapshot of it, which basically says that the red cells are all channels not available in those cells. The green ones are completely available. The 100 basically means 100% available, and the yellow ones are partially available. But for our study, we actually considered the yellow ones as not available, so that's considered a step by us. And these are the cell index, and available channels and available megahertz. So we use this sort of a database actually see how much white space is available.
So you made the partial also red in your study?
Yes. In the last calculations that we did, we all made the yellow ones all red, so we didn't use it. Although it might actually be better to try to use it, but to be conservative, we just omitted it. So now we want to try to apply these white spaces that we know are available into a use case. Use case for us would be a backhaul for internet traffic, internet data. To illustrate about this, so by any means, if any device connects to any of our proposed towers in our system, this is our part of our system. Wherever, however, basically they connect to our tower here, we use the white spaces to get these data to whatever node they are looking for, to their destination node. So it travels through the backhaul network and reaches, for example, a fiber point that it's actually trying to reach. And this is basically for places that do not have this kind of connectivity, and in rural places or places that are less densely populated and do not have high-speed internet. For this system, we actually used New Jersey for a couple of reasons. Well, first, it's near two metropolitan cities, which are very, it's a very interesting use case to see. And secondly, it's the highest population density state in U.S. and again, an interesting fact. And of course, we're New Jersey. Again, we use this 5 by 5 grid that we have. So we have cells of 5 by 5, and we have about 307 of those. And so presumably this would be how it looks like. So antennas in all of these, middle or near the middle of all of these cells that we have. And so these are FCC requirements for these antennas. They cannot be higher than 30 meters. Their transmission power should be limited to 4 watts ERP. And we're going to use, since these are fixed devices, we're going to use fixed device rules instead of fixed device rules from the FCC rules and regulations. So just to look more into it, this is how it would look in terms of the routing strategy. So it would actually find a route to reach one end user to a fiber point that's either already in place or we have it in our system. So it's not going to be, it's basically going to be a mediary way of getting these clients that are not do not have access to fiber somehow through white spaces and connect them. And if you zoom in a bit, we can see that we propose to use 4 sector antennas instead of 1 omnidirectional antenna. This way we have more concentrated transmission and basically longer paths with higher SNR. And this is how it could look. And next we want to talk about wireless microphones. Although we know that the new sets of rules do not actually concern themselves of wireless microphones. They basically have channels available, and this is not considered in the new rulings, but it's interesting to see how it affects our system, so we just had it there. So the previous ruling says that we have to sense these wireless microphones or any low power devices at minus 114 dBms. And well, the new ruling says just give them one of those 36 or 38 channels and just forget about it. Our approach is basically whatever the rules are, this system can still survive. So to justify that, we have a couple of calculations. So the transmission power of a wireless microphone is about 50 milliwatts, which is 17 dBms. And that means that we need a maximum path loss of 131 dBms based on their requirement there. And also we add a 10 dB factor into it because of the building penetration, which is a very conservative number again. Taking all that to account and using the HATA's suburban model for this and for UHF channels only, we come up with 1 mile radius around the tower that the wireless microphones will actually be detectable based on the rules that we have. On the other side, the dominant wireless microphone users for this use case came out to be churches and schools. And in New Jersey, we have about 2,500 schools and 4,500 churches. So this is where we're going to go for the statistical analysis. And in that 1 mile radius, which is about 3.14 square miles, we're going to have 1 school and 1.8 churches, just to be exact. So that means that potentially there might be 3 channels occupied by these 2.8 users, basically. But there are a couple of things that come into play here. First, well, there's a high probability that these users are going to use the same set of channels because they're going to have the same, similar equipment, and they're going to use the same channels, basically. So they're mostly going to congregate in 1 or at most 2 channels. So it's not going to actually be 3 channels. And the other thing is that if we know where the schools and churches are, we can just change the positions of our towers to just avoid them, sort of have a hole for them in the system. And also, where we propose the system to be work better would be the rural areas and the less dense areas. This calculation is for an average, which would be presumably more than what we're going for. So the rural areas would have less number of schools in them and less number of churches. And lastly, they have different peak hours and internet usage. So that's not going to affect our traffic that much. So internet usage is actually 9 p.m. to 1 a.m. the peak hours, or 9 p.m. to 1 a.m. at night. So, and on the other hand, schools and churches are mornings and evenings, basically, or like holidays or something. So again, these won't clash. And also, on the other hand, it won't actually pose any danger, we claim, because our system is going to be a system of 30-meter antennas, 30-meter towers, talking to each other directly through directional antennas at a height of 30 meters. So, and on the other hand, wireless microphones would be on ground, and so the effect would be very negligible.
So you see a lot of cellular antennas along the turnpike, for example.
Mm-hmm.
How tall are they? Which ones do you see? Like there's one right near Ryder's Lane.
I'm guessing it's more than 30 meters.
It's not clear. Somebody said, oh, they're 30 meters.
30 meters is like what, 90
About
feet?
100 feet.
100 feet, right? So
Maybe more than that.
they're probably, for instance, if you see the ones on Garden State Parkway, they seem more than 100. Like, those ugly
trees.
the fake trees, they're more than 100 feet. But then I think there are different kinds. Like I see some in East Brunswick that are probably not 100 feet, they're like probably shorter. I think it depends on the zoning. But I think on the freeways, the ones you're talking about, I think are probably more than 100 feet.
They seem 100 feet seems pretty tall to me in most of New Jersey.
Yeah. Well, I guess that's what we also assumed here. So.
Yeah. I was thinking more in the context of this network being an eyesore.
Oh. We can use those trees if it makes any difference. All right, so this is basically what we shoot for this feasibility study. So we want to calculate the achievable capacity by the limitations that the FCC has given us, and on the other hand, an estimate of the demand that might be there in each of our cells, and try to compare these with each other. If our achievable capacity is more than the demand, well, we can use white spaces and we're good. If not, we have to use fibers. In those cells that do not have this requirement, we use fiber. And along the way, we use a couple of resources some of them are noted here. So first, the achievable capacity. To calculate the achievable capacity, we actually have two elements in there, the available bandwidth and the spectral efficiency. For the available bandwidth, we actually have our database there. But just to note again, we have 7 to 31 channels per cell, so we have exactly how much bandwidth in megahertz we have available. And a couple of interesting things is that we don't have any islands there, so we don't have a cell that only has a couple of channels and no cell around it has those channels available. This would basically mean that that channel is useless because we can't actually transmit anything. And on the other hand, we have similar channels available in neighboring cells, which gives us interference if we want to use those channels. So to actually try to mitigate that, we use frequency reuse plans. So this is an illustration of basically how the path loss would look in our system. We use the ITU model, and we use obstruction heights of 15 meters basically, and along the path, and we consider this as a line of sight communication. And so we have two different heights of these obstructions actually. So we have a 15-meter height obstruction and a 30-meter height obstruction, which is basically for dense populated areas and lower population areas, sparse population areas. And along, in addition to that, we have a 1% outage with an 8 dB shattering variance along that path loss. So this is how it looks in terms of the figure. And for example, if we use the reduced factor of 2, this would be a path that might be taken. So the green ones are one group, and the red balloons are another group, basically. And as you can see, if we use this reduced factor of 2, this is the SNR received at the first. For example, if transmission is from cell 1 to cell 2, this is the SNR received at cell 2, which is 19 dBs. And the unwanted interference, basically, right here, would be whatever is received at cell 4, which is using the same group of channels. But this would be 5 dBs. And compared to that 19 dBs, there's a 14 dB isolation if we use a reuse factor of 2, which is assumed to be good enough for us to rely on. So we have the bandwidth database, and now we go for the spectral efficiency. So for the spectral efficiency, you actually need the received SNR to calculate that. And the received SNR is based on transmission power, which is limited by the FCC at 4 watts. We have the noise, which is basically thermal noise plus a noise figure that we add ourselves. And we have path loss, which we use the IQ terrain model for that. And the formulas for all this is in the appendix if needed, I can show. So an example of this would be, for example, let's consider a cell over there. If we do the calculations for that particular cell, we have 9 channels available in that area there. And after the reuse, it would be cut in half, so it's 27 megahertz there. And the spectral efficiency in that region is 6.23, and it's been dependent on the population and the height of the obstructions in there. And so the maximum GEO capacity comes down to 75.7 gigabytes per hour. So this is how much we can deliver. This is a snapshot of our database. That was for one cell, so if you do it for 300 cells, this is how it would look.
So do you think it's better to talk about data per hour than data per second?
The reason I did that was that the statistical data that was available to me for the demand, the other part, was all in megabytes per hour. So it would be a fair comparison to fair use. That's why.
So you're going to talk about that one, right?
Yes, it's in the other side of the equation. So now there's a demand that I'm talking about. So, well, the first thing, the 2 factors that would affect demand would be the usage per household and the number of simultaneous users. Well, using it at the same time, basically. So for the usage per households, first we have to see how many clients we have, or how many households we have in each of our cells. So the first thing we did was a population estimation, basically. So this was the population density of New Jersey based on the U.S. Census 2000, and approximation would look like this. So we used that approximation for our estimations right now. This is basically 10 different grades of population. So now we have the population per cell, and we statistically say that 3 people per household are living per household. So if you want the number of households, just divide by 3. And also we know that about 74% of the people actually have internet and use internet. So
is this for New Jersey or
this is national. Yeah, these are national. So at the end, we can actually calculate the number of clients or households per cell. And using the Cisco survey that was, I think, conducted in 2010, they have these 4 different. They actually have this one number here. They say that the peak usage of internet around these days would be about 18 megabytes per hour. And we basically went for more future numbers, and we used 90, basically 5 times that, 7 times that, and 10 times that. It comes out to 180. And also on the other hand, we have the simultaneous active users, which means that how many of these users were actually going to use internet at the same time. So we have 3 different parameters there: 10%, 30%, or 50%. So again, coming back to the same example, cell. Population, we have the population, we have the number of households, and the number of internet connections that we have is given there. So as an example, we take that simultaneous users to be 30%. And it comes down to the 4 different scenarios we had, comes out to these 4 different numbers. Again, a snapshot of our databases would be these 2. So this is a snapshot of the internet users per cell. And after that, we have 4 different scenarios with 4 different usage per hours for all our cells that we have. So coming back to our example, so the first scenario was a 30% and 18 megabytes per hour link. In this case, our GEO capacity is more than the demand. So it's fine. We can use white spaces if we have this scenario at that cell. The second scenario would increase the usage times 5. Again, we're still safe. We can use white spaces in that scenario. But in this right here, we actually have less achievable capacity than demand. So in this situation, we have to use fiber in that cell. And of course, the same goes for more megawatts per hour. Again, we have to use fiber because we don't have enough achievable capacity. So gathering all that for all these 307 cells would give us these numbers right here. So for different usage, simultaneous usage, and for different hourly usage rates, we have different number of fiber we actually need to illustrate this. So the 10% would look like this. Of course, you would expect that all this would be around New York, and it goes into some around Philadelphia there. This is again for 30%. As you can see, it's growing, and at the end we have the 50%, which looks like this. And
so do you have a plot of how the current fiber distribution in New Jersey looks like? This is sort of what you're saying, right?
yes,
You can't do backhaul in those red areas
yes,
with white space.
yes.
So do you know how the current map looks like? You think it sort of looks like that?
I would believe so, yes, because it's. I mean, these places are obviously just as just as populated as New York. They would definitely have broadband internet connections, and I'm guessing it should be like this. Well, the proposers we propose over here that even if it's not available, we cannot support it, so we have to implant fiber there. So all this is good, but it has one more issue that we need to address, which is from all these calculations, we now know that we can, based on these illustrations and everything, we know that we can take this traffic from one cell to another. But what if the actual destination of that data is not the neighboring cell, it's another cell? So, in other words, we have determined that if somebody connects to this tower, you can easily go to that tower if it's in that white space region. But what if there are a couple of more, what if the destination is another cell, another tower, and there are a couple more users trying to connect to the same tower to get to the same destination? Then this would not actually ensure a complete success for reaching the destination. So for that, we have a couple of proposed solutions. The first one would be to use the excess capacity. So excess capacity is the capacity above the demand. So that in that comparison that we have achievable capacity, and on the other side we have demand. If the achievable capacity is more than demand, we actually went back and studied this, and it turns out that if it is above demand, it's above demand by a very significant amount. So the excess capacity, the achievable capacity above the demand is a considerable amount. So we can use that for routing traffic. So on top of that, we can use clustering techniques to have a cluster around these group of cells to basically lower the hops of any routing. And along that, we can actually have cluster heads as fiber points. So we can plant a fiber there if needed, and then all they need to do is just go through 2 hops, for example, to reach a fiber point, and then from there, just connect to another fiber point. An interesting thought about this would be to plant these fiber points at the cells with the most capacity available. And in doing that, they would have they would have the most ability to actually handle whatever traffic is thrown at them. So having said all that, we still would it would be interesting to have a detailed routing study.
Chances are, though, right, the planting the fiber, right, is cheapest in the places where the fewest channels are. Like the fiber is most likely available in places where most of the people are.
Mm.
The people are is where the channels are fewest.
Sure. Well, as you're going to see in the next slide, it's actually not that much as an example. So let me just show you that. So over here, this is an example of how it would look if you wanted to deploy something like this. So these are like 8 clusters that we have. So they are, so for example, we have 1 fiber in each of them planted. So this is about 8 fibers extra. And then we can come up, this is again a very first order study, but we can come up with very like more detailed studies basically on this. But
these pictures are kind of awesome in some way because, you know, if you did a first order study of where do the people live in New Jersey, the red boxes are where the people live, and the gray boxes are where nobody lives. Literally, I bet the density in the red boxes for people is 10 times higher than the gray boxes. Well, I think Sam lives in that bottom red box down there near the 4. Is that where you live? Right?
Where you're living, kind of on the border between 4 and 7.
Right, I'm saying that little box there, right at the bottom. The one right
Between
in the
4 and
4.
7.
Yeah,
The
that-
4 and 7 is a lonely little tag of a box.
Yeah,
What town is it?
It's close. It's a town called Siglinville, New Jersey. It's
Yeah.
What's it called?
Siglinville. It's
Sicklerville?
yeah, close. It's basically on the Atlantic City Expressway between Philadelphia and Atlantic City.
Yeah.
So it's down on the expressway. But no, it does drop off substantially when you.
There's no one who lives
Because 7 and 8 is the Pine Barrens, so it's kind of you're enforcing the fact that no one lives there. So that's kind of a whole interesting dynamic.
And 1 and 2 and 3, like along there's the Delaware Water Gap, and it's all mountains, and it's also all empty. So I can never figure out whenever I hear this, is this a really good complementary solution? That in fact you get 2 benefits in these areas. Like one is there aren't any TV channels because no one wants to put signal where there aren't any people. And then 2, there aren't any people. All right. And there's a third benefit. I think that, except for maybe in the Pine Barrens, the real estate might be relatively cheap. The rest of New Jersey.
well, that's I guess another future analysis.
No, I think this seems like a really good solution for New Jersey. I'm not sure how it will work out for the other states. But New Jersey has this sort of very peculiar
Yeah.
sort of interaction
This is
between
the
New York
map.
City, yeah.
Yeah.
I think it's
Where-
really cool.
Okay, so please, I'm sorry to interrupt.
So if we cluster these available places for white spaces into 8 clusters and propose to have 1 fiber point in each of these clusters, then those 8 right there that we added. So now we have sort of an algorithm to follow. So if the excess capacity that we have is greater than the total demand into 2 and 3, 2 or 3 basically, and the 2 or 3 comes from, well, if we have a fiber point in each of these groups, they're not going to be more than 3 hops to reach your fiber point, so you don't need more than 3 times the demand at most. If we consider that as our routing traffic and compare it with the excess capacity, if the excess capacity is more than that, then 1 fiber is fine because 3 hops are fine, and so we can use only the 8. If not, we just add another fiber to there to sort of try to lessen the number of hops that it actually has to take to get to fiber. So this example is for the 30% active users and 126 megabytes per hour, which is on the high side in our calculations. And this comes down to only adding 10 more fiber cells at in the whole system, which is a small number of fiber points to add. What we did right now, come to the conclusions. So we did a feasibility study on our case study, New Jersey, and all the most of the factors, most of the numbers, calculations used in this study were conservative, and the results are of course pessimistic, but still they're reasonably promising. It would be definitely cost efficient. Basically, it would be more cost efficient than laying out fiber in all these points. So.
But you don't really know that. In the sense that, like, unless you did a thing where you figured out what the cost of putting up towers is,
Yeah.
or renting tower space in these places, I don't think you can assert that. And also the cost of, well, what's the cost of bringing fiber to a location? I mean, somehow the cost effectiveness.
We don't have an
depends on both
analysis
of
to.
those.
Just
Yeah, well,
back then.
yeah, I guess that's right. But I would assume that lining out fiber in each of these cells and reaching to each and every house would cost a lot of money, wouldn't it?
Well,
I mean, right, with white spaces, you're just basically feeding a whole,
So
cell.
he's saying that in these rural areas where the population is sparse, running a fiber to every farm or whatever you see.
Because if you want to lay out fiber, you're going to have to lay out fiber to each and every house. You can't just lay out fiber to someplace and then use another.
right, but even still, right, you want to deploy all of these towers, right, for fairly, for kind of constrained data rates. Like, so that the data rate that's handled by a tower is limited by your available spectrum, right?
Yes.
And even on a per tower basis, if you actually went and priced out, well, what's it cost to get a tower in a place, right? And now it's playing 120 megabytes per hour. If you thought about what kind of revenue stream that generates, it's not clear that the tower is viable.
Yeah, I guess you're right. If we want to actually assert this, we have to go into
Yeah.
cost-benefit analysis. But what I assumed was that, well, fiber is going to have to go from door to door. And especially in these areas, it's going to...
So this sort of goes into the premise of why they opened up white spaces. Right? One of the big footnotes was that this is supposed to provide infrastructure to places where there is none because it's not, apparently laying fiber there was not viable.
So New Jersey, in that sense, also might be odd, right? Like you have, somehow, right? The question is, is there fiber wandering through the Pine Barrens, like along whatever the Atlantic City Expressway, right? And the answer is probably. I mean, everybody on the has an expensive home at the shore has some kind of fancy Comcast service.
Yeah, but then it might be good, right? That if it's there, then you can just put a cluster head there and get it to all these people who are not the wealthy people who live shore.
Well, I guess the conclusion is that it's not that clear, but
Yeah.
our proposal is that it would be, so...
So how hard would it be to adapt the routing or whatever to avoid sudden increases in wireless microphones? Like, for instance, if the Giants are playing in the Meadowlands, there's a ton of wireless microphones in that.
Well, places like these stadiums and convention centers and all that, they actually have licensed wireless microphones, I believe. So,
I see.
So that's not a problem.
I see.
And then
So
plus the new
It's
ruling,
only the schools and churches, it's the low-end users.
and plus the new rulings actually, the new rulings gives them one channel and tells all of them to tune into that channel only.
I see.
And if you are out of that channel, we don't care about you. So, I mean, and in this system, actually, we would be affecting them more than them affecting us.
Okay.
So, and well, again, the same conclusions that we already made. It's going to be most effective in rural areas where we don't have internet connection. Presumably, there's no fiber infrastructure, and there's more available, more bandwidth available, and better penetration there. Some future work would be, if this study would be to get more complete, we can actually go and take a deeper look at the new ruling for the wireless microphones and low power transmissions, and see how exactly that affects this system. And again, we at the start of the study, we didn't use LPTVs and other licensed but low power local transmitters into account in our database. So we can just add that as another future extension. And the routing strategy that we just showed as a first order study could actually be a detailed study of routing data. And as Professor Yates mentioned, a cost-benefit analysis would do great here. And a couple of extensions to this work would be, well, we can extend this to a national study, so not just studying New Jersey, and we can actually, it would be interesting to see how this works out in other states. And along that line, we can actually do a more detailed path loss model for different terrain conditions and different populations. So that's it. These are our references, and thank you. If you have any questions.